So good afternoon, and thanks everyone for braving the snow to get here. We're honored. We're honored to have a tag team of two of our EOL staff for giving today's EOL seminar. Mike Daniels, the head of our CDS,
Computing Data and Software.
Computing Data and Software, and Charlie Martin, who's also in the group. And Charlie's distinguished by having this year received the NCAR UCAR Outstanding Achievement Award. You're number 6 in all of UCAR or something like that. That's not handed out very often.
I wasn't counting.
Something. Anyway, they'll be talking to us about new ways to collect data.
Real time.
And so I'll just go ahead and start.
Thanks, Steve. Okay, first thing I want to say is I'm the principal investigator of this award. It's an EarthCube award, and so this is the team. These are the team members. So I'm representing the work of all these great team members we have. So with that, the CHORDS stands for Cloud-Hosted Real-Time Data Services for the Geosciences, and so hopefully by the end of this presentation you'll understand what that means. Real-time data is critical and growing importance. We know that very well in the observational community. There are real-time measurements of floodwaters, real-time tweets that describe hazardous events, and then of course in EOL we do a lot of these field experiments where we're trying to observe a dynamically changing phenomenon, and we have aircraft, we have radars, we have surface instrumentation that we're trying to coordinate around that storm to take the very best measurements. And of course, real-time data is really key to that. We need to get a good picture of the situation in order to assess it. Same thing happens in the oceanography community, for example. So there are kind of episodic real-time events like our field programs, and there's this sort of measurement of the ambient condition to detect events that occur. So I don't know how many folks know about this, but there's this concept of the Internet of Things. It's essentially saying that many more devices are going to be connected to the internet in the future. Your watch, your phone. I'm a fisherman. I decided to replace my 14-year-old fish finder, and it has an internet connection, and it uses it to download maps and to send position data to a crowdsourced map. So this notion that many more things are going to be connected to the internet is one thing that's driving the importance of real-time data. But of course, watches and not everything can be used by the geosciences community. So we're really focused on geosciences things, and that might be a surprising area. Things might pop up in areas that you may not expect. For example, we were at the AGU last December, and there's a fellow at Berkeley developing an application called MyQuake. The gaming community is developing accelerometers and really fancy capabilities in these phones, but they can actually also be used for things like detecting earthquakes and trying to help put those data into another crowdsourced model to predict where they'll go. So I think that the Internet of Things is going to change the way we think about the everyday devices that might be connected to the Internet. Dan?
So crowdsourced usually means that people are funding it. But you mean now crowdsourcing crowds are providing data?
Exactly. Yeah. In this particular case, the application called MyQuake runs on your phone in the background and reports data. So you do have to have have that app installed and running. In fact, he told me that one of the early designs of this had challenges in terms of the battery consumption. So I'm not saying these are easy problems, but it is a different domain. With all of these devices connected to the internet. So EarthCube in about 2012 decided to do domain workshops. So geosciences domains being the oceans, the hydrology, atmosphere, solid earth sciences, and Vonda and NSF asked what workshop might be appropriate for our domain, the atmospheric sciences domain. And I decided to think about it a little bit differently in terms of a technical domain that I thought could cross geosciences. So we got funded to put on a workshop for real-time data in June of 2013. It was about 70 to 80 folks around the geosciences that came and gave us their ideas, their projects, and we generated a report. Some of the highlights from that report are that there needs to be improved community infrastructure. Everything from communications from the sensors to the internet to on-demand computing and protocols for data exchange. There was very little metadata being generated for these streams. They just sort of popped in and you sampled them and displayed them, and there was no tracking of the provenance of where these data came from, and metadata describing the measurements in more detail. The community felt that we needed tools to integrate and display these data from differing time and space domains. Things are coming at very different rates in very different parts of the world, and to have one infrastructure that could kind of assimilate that and use that in an effective way was something the community needed. And then along with real-time data comes the actual control of the instrumentation at times. So in our case, we have an aircraft flying, and I wouldn't say control is the right word, but guidance to where the aircraft flies is another important aspect of real-time data. And of course, in many sensors, that can be done in an automated way, and EOL has examples of that as well. And then we want to integrate some of these real-time data with the folks that are actually doing emergency management. An example I heard of at the ESEP meeting in January, we're using UAVs to do a sort of a photographic survey of damaged areas to try to help the emergency managers target the areas that really needed attention and ignore others that looked okay. So that's a real strong connection in terms of hazards and things like that. And then the whole area of social media, apps, and crowdsourcing was another identified need from this community. As I was saying, you're going to have there are many more devices that are going to be connected to the internet in the future. So that's the summary, some of the highlights of that report. It's all available online. I'd be happy to share that with you. And as a result of that workshop, we submitted a building block proposal in EarthCube. Now, EarthCube, if you don't know, it's an initiative that covers the geosciences. They have both building blocks and then what are called research coordination networks, which are more like workshops, to gather feedback. Building blocks are actual tools or prototype tools. And so we submitted a proposal in 2014 with these areas. We identified that real-time data has some unique challenges compared to the retrospective data, and it's really important to get it right as you do the sampling, because otherwise, the data downstream is of limited use unless you take very good measurements in the front end. We wanted to use a cloud-based infrastructure for this, and we understood that there are many real-time systems around in the geosciences. EOL has some. There's an IRIS group that does seismic sensors. An oceanography group also has sensors on ships. And so in those cases, we would fork those streams. Stay going. The data would stream to their existing systems, but then would fork to CHORDS so that it could be accessible by a broader community. Less overhead and simpler access. And one of the things we decided to propose is using some standards. This Open Geospatial Consortium has a whole standard directed at sensor webs, they're called, so these webs of sensors, and connect some of our streams to those standards, and that would provide some metadata, make those data more useful. That was part of our initial proposal. And then one thing that we hear from our scientists here is they would like to get access to our real-time streams to actually do algorithms, compute, let's say, the next trajectory of an aircraft or where to send the vehicles that are chasing storms. And so the scientist community would want access to the real-time data in order to connect those to their own algorithms. And then, as the EarthCube community developed, it had several building blocks. Some of them, dealt with models. Others were, post-distribution. Others were like discovery. So we wanted to connect real-time data to those services so that a person could discover the sources of real-time data that are available through the CHORDS mechanism in the geosciences community. And then there's a fair amount of work being done in this adaptive sampling area where, as I was mentioning before, you can control the instrumentation based on the inputs that you're receiving. So, doing this in sort of an automated way, and I'll give you one use case for that. And then finally, connecting these streams to these decision support systems and making them very diverse. So these are the main topics of our 2014 proposal. The partners that we chose to work with, Chandra is a research scientist and engineer at CSU. He's doing a project down in the Dallas-Fort Worth area. They have these radars that are very small. They fit on cell phone towers. They're called CASA, part of the CASA network. And so their project is to estimate the precipitation in a cloud and then send those estimates to the downstream hydrologists, who will then predict what areas will flood. So he had a lot of exposure and experience with adaptive sampling, because these small radars actually track the storm as it moves, and so they'll point in the direction of the storm, and then another network of these will take over. So he had quite a bit of experience in that area. We also has a partner, Branko Kirkez. He is working in a group in Michigan. He just finished his PhD. It's a small group. It's him and a couple research assistants. They're doing adaptive sampling with water quality measurements. And so one of the challenges with these water quality instruments is they're solar powered, so they have to be careful with their power consumption, and actually they routinely do a slow sampling rate to sort of save on power. But when an event comes, a flood event comes, or something like that, they want to sample much quicker. So what he's actually developed is something that goes to Weather Underground to get forecasts to tell his instrumentation, in these streams, to start sampling faster. So he had experience in this adaptive sampling area, and he's also an early career researcher, so he was brought in as a partner. Frank Vernon is part of this EarthScope project. These are seismic arrays that are moved across the United States. So he had the solid Earth experience. He also had a real-time system already in place that we could use as a test bed for forking data into CHORDS. So that was his contribution to the project. And then we had the UAH group, who was very engaged with this sensor web enablement system, and connected to many of these other end user tasks. And so they were enlisted as a partner as well. They had the experience with this Open Geospatial Consortium standards, for example. Here in EOL, our contribution, this is an example of what we show in the field. It's a situational awareness display of aircraft. We have the live video coming down from the aircraft during missions. We have satellite data, radar data overlaid with the tracks, and we use this to guide the missions. One thing about this display, there's a lot of capability. We have a lot of different overlays that can be added, including models. But the data itself, the streaming data from the aircraft, is not accessible through this display. It's more, like a closed-circuit TV that you can watch and you can configure, but the actual data are not accessible through this, and so that was one need that we had in this project. So we wrote up a couple geoscience use cases. One of them is evaporation of water and assessment of its quality in the Great Lakes region. So this would be a project that would have hydrology instruments needed, an aircraft that would measure evaporative fluxes across the lake, buoys that were in the lake itself, and so it was a nice case of geosciences, real-time data measurements that would help the scientists understand this problem. Another use case was in the seismic area. About 2011, Frank Vernon came and talked to us about the time when they had the EarthScope network out in the Midwest, and they actually saw a signature from a tornado from these seismic sensors. So that's not something that our atmospheric science community thinks about much, but there's some interesting data and use cases that can be developed from that fact. And so he gave a talk about that signature, and could those sensors be something that our atmospheric science researchers use?
And this is atmospheric pressure, Mike?
Yeah, it was pressure. Mm-hmm.
They were measuring seismic.
Right, but they also have the state parameter pressure data as well. Yeah. Actually, they have little meteorology stations that we could tap into, and in fact, they had a lot of questions about the instrumentation that we use to help improve their quality. So we did submit the proposal, but we got approval for a scaled back version. It's essentially what we decided to focus on instead is just exposing this concept to the broader geosciences community. that you can actually develop a common, real-time data system that could apply to a lot of instrumentation across the geosciences. We proposed to start adapting and testing some diverse real-time streams beyond just atmospheric science sensors. And then we would test this Open Geospatial Consortium SWE infrastructure with these streams. And then one other part of our proposal is that we connect our streams where possible to these other existing building blocks as part of the EarthCube ecosystem. So we began by focusing on these very small measurement teams. As I mentioned here on the left, Branko Krkez is a recent PhD graduate. He has 3 research assistants, and they don't have a lot of resources, but they're pretty good at the measurements that they're taking. They're good at building instrumentation. A more recent group that we're working with is this group here at NCAR and RAL and JOS, who are developing these weather stations that are printed with a 3D printer. All these components are printed with a 3D printer, and they use Raspberry Pi computers to do the sampling of the data. You can get a weather station like this for $200 to $300. And their objective is to put these in developing countries, as a very inexpensive way of getting some meteorological information. But again, it's a small team with not a lot of resources for the downstream uses of their data. So we started by focusing on these kind of users. And the characteristics of these users is that generally they're experts in their unique measurements. They're frequently looking for funding, to keep the programs going. They're really not able to focus on this complex standards and OGC infrastructure and things like that. They're really focused on the measurements, and so they don't have time to deal with these complicated documents and standards. And they really lack resources to spend on expansive hardware and software. They're really focused on acquiring the data. But of course, they'd likely see benefit of the more use of their data. So that's the nice part that we can add with CHORDS, is to expose their data to a broader community. So here's the general model for CHORDS, what we had come up with. You would go to something like the Amazon Web Services, a cloud provider. You'd see a little acronym. I had to paste this in, but this is our vision. An acronym for CHORDS, getting your own CHORDS instance. You would download that instance. It would be running in the Amazon Web Service. It actually fits in what's called a micro instance, which is free for the first year. After that, it's 50 cents a day. Is that right? So very inexpensive. They don't have to go to their IT department to ask for resources or create a virtual machine. They just do it on the cloud. They configure their own portal with their instrumentation, describe it, add as many sites as they want, and then start getting their data coming in. So that's the 3-step process. And actually, it turns out, obviously, there are steps in between each one of these. And the first one to get the Amazon instance is about 8 steps. Is that right? Something like that. And then similarly, when they configure their instrument, they have to type in information about what they're measuring, the variables, and that kind of thing. And then they get their CHORDS portal. So that's the basic concept. A couple of the reasons that we decided to use the cloud and virtualized servers is scalability. If you have a very large network, you can scale that up very easily. Everybody knows that's one of the benefits of the cloud. You don't have to access your friendly IT department. It's your instance. You can configure it at your own will. Basically the cloud services are ubiquitous. They're all over, and so it's something that is very common and will be commonly used. And then there's this notion of DevOps, where the developers are also like the sysadmins, for these systems, and that makes the cloud services makes that very easy to do. It's easy to deploy software in the cloud, which is one thing we found out. And then these development environments can be generic enough to work on many different cloud providers. It's pretty agnostic to what cloud provider we would use, and then that makes the software easier to install on many different systems. So when you've got your CHORD instance going, the next thing you want to do is start sending data to it. And so we've given a couple examples in Python and in wget, but it is as simple as typing a web address with the variables and the values in your web browser. And of course, most scripting languages can send an HTTP request. I'll break that request down a little bit so you can see what I'm talking about. that first host name is your portal address. You have an instrument ID, if you have several instruments at your site, and then the wind direction is 121, the wind speed is 21.4. Those are the actual values that you're inputting into the system. So you type this into your browser, and you've just entered 1 point into the system. So what you do is connect that up to your sensors, have it start spitting out HTTP requests each second or each some period of time, and that's very simple for folks to do. This is how you get your data into the system.
But how do you get your instrument to do that? I know how you type it in, but what does your instrument need to provide that?
Yeah, and in fact. We have quite a bit of experience with communications, but that can often be the weak link. If you don't have cell phone coverage or something like that. But of course, you could use a satellite connection if you want. So we do assume that there's some basic data communications capability, and in fact, I think we've helped them understand what's available in some of those cases. But yeah, you do have to have a basic internet. You have to have a connection to internet. What do you want to say, Charlie?
And Jeff, also, instruments all have computers and running software. And as Mike was saying in the previous slide, you have a little Python script that does that. Can you go back to that slide?
Sure.
That just does that. You see those 3 lines of code?
The red.
So you have to write a little bit of code to do
So
that.
you provide help with that code?
Yeah.
Well, you have examples on the website.
Okay.
Yeah. But that is a good question. You have to have basic connectivity. Yep.
So
Dan.
this key, I don't know whether that's
Oh,
meaningful
okay.
and also
Sure, mention that.
authentication.
They're related, actually. Yeah. One issue is if you just had the URL, then anybody could send a point to your CHORDS portal, and so the key is a security mechanism, a unique key for your portal that you have to include. We just scratched the surface at security, but we did build in some, and we know that that's going to be something that we want to expand. Yeah.
Just curious, is this all point-oriented data?
It is.
This appears to be focused on.
Yeah, exactly, and that's part of one of the things we had to do in the scaled-back version. We wanted to do more spatial data, but in the scaled-back version, we focused more on the time series data. Thanks for that question. So we came up with this idea on our own. We thought we were pretty smart, and we were in the project, and lo and behold, there are tons of companies that are actually doing this. They're really working on it from the perspective of the Internet of Things, the toasters and who knows what else. And so, but there are plenty of these around to highlight sort of the distinguishing features between us and them. These commercial groups is the portal is completely owned and managed by the science team. These other services, they have a server that you send your data to, and we'll give you your data. So they like to centralize, the services, and ours really lends itself to being in a distributed network model and not a monolithic server. Our software is on GitHub. It's open source, so it's not tied to one vendor or company. There's no monthly fee other than this fee I told you about for the hosting of the portal itself, which is around 50 cents a day after a year. It's an open source project, so you can actually download the source and add some new capability if you want to. And then it implements OGC standards, which are really important from the geosciences community. There's this thing called sensor ML, which basically describes a sensor. It's just an XML object that describes a sensor, and CHORDS will output that information so that it can be registered as a sensor that's available for the geosciences community. And then, of course, we're connected to all of this infrastructure that EarthCube brings in terms of exposing all the real-time data sources in the geosciences and that sort of thing. So we're really focused on geosciences and really the academic kind of environment. So that distinguishes us from these commercial outfits. And with that, I'll have Charlie do a demo. Sorry. Yes.
A couple questions. Data storage on the back end.
Mm-hmm.
How large and
Very good question. We have the portal. Each portal has a database running, and it has limitations on the number of points that it can accept. It's 1 million, or is that more now?
No, more
More than that now. We're not an archive. It's not an archiving system, but that has been a common request to somehow connect this to something that's also recording an archive. And so on the database limitations, we sort of flush the database periodically and then start over. So it is an existing limitation. Yeah. Yep.
And then access control, you mentioned for entering in data. What about the ability to limit access?
Yeah, so the portal has logins and passwords. So, that's all, again, within the control of the team. We give them a default admin account, and then they can add as many as they want after that. Yep.
Just curious, the 50 cents a day that you're mentioning for the micro instance,
Yeah.
that's just the instance, that's not the bandwidth. Is that correct?
For the kind of data we have here, our bandwidth is in the noise compared to what Amazon wants to charge you for. Yeah. When you do the cost estimates on Amazon, that doesn't show up.
It's bandwidth going out, not in, right? Yeah, that's a good point. I'll help you, Eric.
Yeah, it's cheap to get it in, then we try to pull it out.
Yeah.
Yeah, well, but it's still really small. I mean, for the kind of use case that we're looking at, that I don't think would be an issue at this time.
And the other thing I'd say is we're not. It's open source and it's a package that can be moved to another cloud service or even a virtual server. So there's nothing in the architecture that prevents it from running, in other places if that were to become an issue.
So I was talking about, you guys have a Docker container or something?
No,
We're headed that way.
yeah, we're headed that way, but we don't at this time. Okay, so let Charlie do a demo so you can understand. more.
Thanks, Mike. That was a great description of the project. I wanted to emphasize, too, that Mike told you about our initial vision and proposal, and then the fact that we really got seed funding for this project. And it really has had maybe 6 man-months of effort to get to this prototype demonstration. We know that there are lots of capabilities that we want to improve on and add to it. So, but the idea is out there and being productively used by some of our friendly testers. We have a nice website which describes the whole system and how to get started with it. It's called CHORDS RT, chordsrealtime.com, which actually goes to GitHub. And this website is a good place to get an idea of how the project works and get ideas about how you would spin up your own portal and so on. Mike was talking about the steps that you use on Amazon to create a portal, and it really, I've got 8 steps here, but most of them are just click-throughs. So it's really pretty easy to do. And once you get a portal configured, so this would be your own instance that you've created on Amazon, then you can go to the new website that it has created. It's created both a web server and a database connected with this. It's built on Ruby on Rails, and you'd log into that. And this is what the front page of a portal looks like. We call it the dashboard. This is kind of the default place to go take a look at what your portal is doing. And this gives you different time span display of measurements, the number of measurements that have been coming in from your instruments. And the idea is at a glance you can tell if things are working or not. This is not the data itself, but just the number of measurements that you've gotten. This is kind of our testbed portal that we're putting some, we've got the 3 NCAR weather stations going into it, plus the weather station in my house. And it gives you an opportunity to kind of look around. So the dashboard is really the first place that one goes to look and see how things are doing. Mike mentioned that all of the data goes in via URLs. The green banner up here at the top shows you the most recent URL that's come in with data. It's just sort of a sanity check to see how if your system's working. Let me get myself logged in here. And the advantage of a login is that then you have administrative access to the site. Never. Okay, so now that I'm logged in as an administrator, I've got more access. There are more options on the left side here. We have just a few kind of concepts in the system. There are sites, which are places that you will have instruments. Here's a listing of sites.
Bigger.
Okay, I can do that.
Okay.
Yeah, there you go.
How's that? Is it good? More?
It's a low resolution projector, sorry.
Okay, good. So here's a listing of sites, and it's very dynamic at this point. Because I'm an administrator logged in as one, I could add a new site here, create a new site, and here's a kind of visual map of the sites that we've got running right now. There's the Wyoming supercomputer there. Once you've got sites set up, you can define the instruments. And this is the list of instruments that are coming in, and some data about how many measurements we've gotten total on the sites. And for each instrument, you can go then and configure that. This gives you some information about it. And you see here, this is the area where you will define what data streams are going to come in. You define a short name, V1, for instance. Is going to be what's in the URL that comes in. If we go back here, you can see the most recent URL that came in for this instrument. There's V1 equals 9.1, V2 is equal to 80, and so on. And they mean different things. I'm going to go back to the list of instruments, and we'll take a look at one that has variables that make more sense. So here you go. This is the weather station at Foothills Lab, and you can see the short names that were assigned to the variables. And finally, there's a graph at the bottom that lets you take a kind of a look at your data and see if things are looking reasonable or not. This is just a standard web component, graphing component from HiCharts, and it'll update automatically. One of the nice features we've got is that when a research group is setting up a portal like this, they can run a simulator. And for all the instruments you've made, it gives you the simulation capability. If I hit this button right here, it would start sending simulated data to the portal, so it'll start sending simulated URLs. And that way you can test everything even before you put an instrument out in the field to make sure your portal seems to be configured properly. So that's really useful. Let's talk a little bit about getting data out of the portal. There's a real simple interface for grabbing data in different formats, like for the Foothills weather station, I'll go get the CSV data for the last day. Did it run Excel? There you go. So that's the data that came for the last day, and you could choose different days. Function of trimming the database. Mike talked about if the database gets too big, the infrastructure doesn't handle it very well in these small instances. So it's looking like about 3 million measurements is what works on our micro instance right now, with giving us a good enough response time. There are also on the web pages a little bit of documentation about building these URLs that you would use. So you can go over here and you can see this is an example of the kind of URL that you would use to put data into the portal, and this is how you might get data out of it. And let's just try one of these. I'll take this URL and I'm just going to paste that into my browser. And there's the last data point that we received. So you can do that from browsers, but you can also put those kind of URLs into your code. So you could be writing MATLAB, Python, R, any kind of programming language you want, a shell scripting. You could write web pages which issue these URLs and grab data for whatever your application is. So envision that a small science team, let's say a graduate department has got a project going somewhere, and the graduate students could put together all sorts of scripts and activities that could be monitoring and producing analyses and so on, tailored to their kind of research. This portal here is, as I said, is kind of the test bed that we're using. We have about half a dozen portals going now with friendly users. Here's another one. This is the 3D weather station, printed weather station that the RAL folks are using it for. And it really was a very convenient collaboration with them. They had the weather station that they wanted to put out in the field. Their workflow model was that someone would go out in Namibia or Zambia every month and plug a USB stick into it. And we said, well, why not just do it in real time? Cell phone is everywhere in Africa. And that was a great match for them because now their instruments can go online automatically. They can get exposure and distribution of this data immediately. So we've been really excited about working with this crowd. So I think that's about all I've got to show you. Do you have any questions? Jeff?
What's your data rate?
So right now, it's more governed by how big the database is going to get. You could put data in at a 1 second rate if you wanted, but
But like for atmospheric turbulence, you want to do like 25 hertz.
right, no, that would overwhelm the system right now. Right now, our database has one row for each measurement, and we'd like to improve the capabilities for that kind of higher data rate. But right now, I'll be thinking of stream gauges, weather stations, seismic sensors, profiling activities, sounding things.
The G5 time series data is actually
Yeah,
The one low rate.
yeah, the low rate data.
Conceivably, you could batch your updates, though.
Yeah,
Right?
yeah, you could. That's an area that we could look into. Yeah, this is data from the G5 from Orcus. Okay.
So the reason there are gaps is because the aircraft flies on certain days and others. So, but one of our scientists here is accessing the real-time time series data from G5 for his algorithms and plots actually during this field program that we have going on right now in Point Arenas.
And this is a little bit bogus. I didn't have time to organize this. This is all 102 variables that are coming down, which I really need to break up into different instruments. Right now, having to pick one of these guys out doesn't make sense. But it's an example of. It's been great to demonstrate how easy it is to fork data from other sources and bring it in here. So I didn't have access to write software that runs on the aircraft on our G5, but I knew where the database was here, so I wrote a little script which queries the database. It gets triggered by the database on the ground and puts data into this instance. And so we've added a bunch of different instruments and projects, set up portals for them. Steve?
And of course, I mean, with our flux stations, of course, we could be pushing the derived flux.
Absolutely.
Every half hour, 5 minutes, or
Right.
whatever.
Yeah, and actually, we've talked to Gordon about putting a CHORDS hook into Nidus, which would be really trivial to do.
It's a really dumb question. It's really exciting, by the way.
Sorry?
What's preventing, I'm a non-CS person, the scaling this to a cloud-based archive to the?
Oh,
If this is all in the cloud, you've got terabytes of Amazon. So
Yeah.
What's
development time,
Yeah, it's just,
just staff.
Okay, so there's nothing technical.
No, not at all. No, and we keep hearing that they want archive as well. It was really designed as a communication scheme that let people get real-time observations out to the world on the internet easily. And they're saying, yeah, we want that, and we would like archiving. So that's something we'd like to put in, but it's beyond the scope of the current project.
Are there constraints in like the time so that can I put in, say, an hour of forecast or a day of forecast, and then as I put in real data, compare it to the forecast? Or?
So absolutely, you could. If you look at this this is not a good example. If you just send a data without a timestamp, it gets stamped with the time of that it received it. But you can add a timestamp, and I'm going to show you that field. So the point is that you can put data in after the fact,
Or it should be before the fact.
or before the fact. Yeah, that's right.
Your initial URL or Mike's URL had time.
That's right.
Do you have an example?
Yeah, I guess this one's not doing that either. Yeah, let's go to the URLs. Oh, that one's not going to let me do that.
Yeah, I remember seeing
Yeah.
that you can specify the time, but I'm just thinking that it wouldn't block you from putting in something that's before the current time.
That's right. No, you can specify the time, forward or back. It doesn't matter. It just goes in the database with that timestamp. That's a good question.
Is there a few NSF initiative tools?
Yeah. It's the NSF Geosciences Directorate.
Is anyone else, other directorates using it?
The directorate's under Geo only.
Oh, only
Yeah.
So I heard mention of OGC standard sensor ML as the suite. How exactly is that used here?
The sensor ML, you know, click on the sensor ML button up there,
We're
right to the top, third line down.
all right here. Yeah.
Sensor ML is the main.
Yeah, and actually, I mean, you can look at that if you want, but actually, this is connected to a UAH server that handles some of the OGC information, but we haven't expanded that very much. I think what we found in this project is, kind of developing this concept. We got a lot of users interested in sending their data to it, and so we configured the portals. We made that very streamlined. We tested the implementation on a variety of different kinds of sensors, so that really took most of the time of the proposal. But we have connected our streams to some of the UAH ODC suite. It's a full suite implementation, suite 2.0, right?
Yeah, and there's really a lot of promise there. That's one of the distinguishing features for us, is that we want to develop that more, to where a hydrologist can bring up a portal, easily put their data into it, and say, I can also get it out to all of these other bigger services that I know nothing about. We're not there yet, but that's one of our goals. Okay, yeah. One last question.
Yeah, to follow up on that, how much of the richness query through the OGC services has been surfaced through the RESTian interface, so that you can slice and get slices of time or space or things like that?
So this is really the front end, and would be feeding systems that have that capability. It's not built into this capability. And we really wanted to have something that's simple, that's really comprehensible for the small researcher, and then the ability for it to couple seamlessly to bigger, more capable systems.
That actually brings us right to the architecture. How do I get over? Oops. Okay. Tiny. Okay, so yeah, and that you've hit on the architecture for the CHORDS system, and as you can see, all the portals on the left. So these are the things that the instrumentations teams primarily would be focused on, making sure their measurements are coming in, assessing the quality. It's really common for those groups to download CSV files, to do some processing. But then those are connected to more advanced services, just via the URLs that Charlie talked about. For processing, translation, mapping, visualization, and then the whole set of EarthQ building blocks would follow some of these OGC standards. So what you're seeing today is just the left side of this graph. But really, we have to get the data in order for these downstream things to happen, and we really wanted to prove that that a general concept could apply in lots of different kinds of sensors. But that's certainly a development that we want to pursue in the future. Thanks for that question. That's good. Here's an example of, I did talk about the fact that we were putting our data into the OGC SWE implementation by the UAH group, and you can't hardly see it, but you'll be able to see some of the water gauges overlaid with radar data. This is the Geo Explorer application that you may have heard of that follows those standards. So I think the next question we get asked is, why should NCAR be involved in this? I'd say, at a much, much smaller scale, we can develop services that are agnostic to the types of data, just like the FTP. It can be documents, it can be data, it can be images. And so we feel that we can develop a system that's agnostic to the type of data that's applicable to our data and the broader geosciences. That's of benefit to us. We can, by being involved in this development, we can shape what it looks like, and make sure that we have some of our requirements into that system development. This also makes it easier for our scientists and engineers at NCAR to access our data. Right now, there's a range of ways to do that. Some require database expertise. Some have other software that you just download. So we really wanted to target this very simple approach of just URLs, to get access to the data. So it makes those data more accessible to NCAR scientists and engineers here. And then this will be a way for us to gain awareness of other operational systems as we do these field experiments in EOL, for example. It's very common for us to tap into existing mesonets that are sampling data. So this will give us some exposure to maybe these networks of sensors that we didn't know about, but they're using CHORDS, for example. And then there are very common challenges in terms of deploying sensors around the world, especially with communications and things like that, signal processing. And so this kind of builds this network of scientists and engineers that are doing that we can tap into, and they can tap into us, for actual deployments. And then what we really learned a lot about during this project is experience in how to deploy software in the cloud, and actually the advances that have been made in visualization through a web browser. That was something that Gordon had dabbled in at about the same time that this project came up. But this is going to prove to be a very valuable tool and skill set for our future displays. And I really think this is a development that's appropriate for a national center. We're really focused on real-time measurements. That's not uncommon within the geosciences community, and so it's something we can share and lead the community in. So I have that's my presentation. So I just have some questions that I'd like to pose to the group, especially providers and consumers of real-time data. But what are some other sources of real-time data that we might need or might be useful for field experiments? Jeff? And Dan?
I would be happy to work with you in getting MOPIT data in there, but I think that because MOPIT data is not really point source or points, I was thinking about using this as a way of tracking file names, and so that there'd be a time series of our granules. People would find those, and then that would create FTP locations.
That's similar to the use case that the NOAA fellow asked us about, right, with the radar data coming in. Yeah, that's a good one.
I'm happy to work with you on it.
Yeah, great. That's great. Other ideas?
I'll give you one.
Good.
What about, if you've got these sensors in various parts of the world, you'd like to co-locate data that would be comparable in space and time.
Okay.
Such as, for example, radar data that was co-located with the precipitation gauge.
Nice.
The precipitation gauge is in your network, but the radar data is also accessible. But you want to be able to tie a specific piece of radar data to that geographical location and time.
Nice, yeah.
So you come up with a way of doing that would benefit both sensors.
Right, good one.
That sounds like sort of an OGC function.
It does, yeah. Other, Charlie?
I just wanted to, I forgot to mention that right now we're strictly focused on time series data, but a few simple data types that I think will give us a lot of leverage would be some imagery capability. You could post an image, moderate size image every few minutes or something like that. That would be a common use. And then also some kind of profile or sounding data type is another very common sort of array type of data. I think people would find very useful as well.
Okay. Yeah, we had, oh, sorry, Steve.
I was thinking of a field experiment that's more like a emergency management situation on demand.
Yeah.
You know, could people prepare sources and get it all working, and then if the need arises, you just turn on the switch and you start collecting all the information for an emergency management
Oh,
situation.
nice.
A flooding, a big storm like we had yesterday, or
Right.
whatever. As an instance that would just pop up and then start collecting the data you needed to
Yeah.
further advise decision makers, etc.
Great. I was going to say we have interacted with these some of these small research teams that are operating UAVs, and it's primarily imagery. It's what I could, at least the people we've been talking to, but and they use it for emergency management, for example. Chris.
So with imagery in mind, I agree that would be super useful.
Yeah.
But it seems like sending images by a URL is a pretty difficult proposition.
Yeah, we'd need to go to another transport mechanism. That's clear.
HTTP is set up for that. We use the post method. You shouldn't be using GET in the first place. But post, you can do file uploads. It's already supported in HTTP.
Okay. Thanks.
Works great for the ease of use, but not really intended for that.
Yeah, that's right. Now
Yeah.
we kind of hijacked it.
Great. Thanks for that. Now on the consumer side, one thing I would mention here is that Mel Shapiro, a scientist here, gave a talk about what if we could take the aircraft in situ data and feed that into a forecasting model that then predicts in real time where the storm is going to be, using some of those data. It was an interesting concept, and of course, some of the constraints were in getting access to the data. But this might open the door for something like that. What are some other scientific needs for algorithm development or models? Real curious what people think. You have some, Chris?
I guess one thing comes to mind for me, and it's not related to models or algorithms at all, really, but an educational component. For instance, if you're at an elementary school somewhere or a junior high school somewhere, and you want to be able to collect data that's from nearby, whatever's available, what's out there, it would be nice to have some sort of means of going out on a spatial basis and saying, give me what I can get that's
Okay.
in a couple months,
Draw a box.
because we're trying to look at blah.
Right. Oh, nice.
Yeah.
Sorry.
To expand on that, Chris, we've gotten an inquiry from
Terry Eastburn.
Terry Eastburn, STEM Seed, and with the idea that CHORDS can be a part of a K through 12 science outreach project, and it provides that component, which would be cloud and computer science and web technologies. That would be just perfect fit for high school students.
We were partnering with this 3D printed weather station group, for example, so that the school could get involved in the design and the printing, 3D printing at the school, connect a Raspberry Pi up to it, and then have the data, analyze the data with something like CHORDS, for example.
So
Yeah.
it really expands the horizon for that educational part.
Yeah, well, and now that I think about it, even outside of schools and such, for one of our projects, we may know that we're going to have a field project somewhere, and without knowing the things that are available out there, potentially go out and put out a query and say, well, again, we want anything that's in this spatial domain.
Yeah.
Show us what we can get at.
Right. Yeah. That's a good. Yeah, that's what we envision, especially with these discoverability of some of these sources. Scott, you had your hand up.
Oh, I just thought, from my point of view, I think it would be very useful for quality control for remote stations. So you have real-time access to that you might not have otherwise.
Yeah, nice.
Avoid a lot of problems or identify problems and then fix them.
Mm-hmm. And Dan?
I think that we should put GPS transponders in the UCAR shuttles so we can know where they are.
At any given time. Oh, I mean like an Uber for NCAR shuttle.
Yeah. But seriously, it'd be like there's commercial applications like this for real-time tracking of buses and airplanes and where they are.
Yeah, good. That's a good one. Yeah, and we're doing a lot of that in our field experiments with the mobile vehicles, for example. But those data are pretty much in a closed system. Is that right, Eric? Or okay, at this time. Oh, those are great. Thanks. And then I think we touched a little bit on this, but what are some other data sources that would be helpful in real time and useful in real time? Imagery was one. We talked about this notion of, especially with high volume data, finding some way to derive products that would be useful to scale it down that in a way that could be more manageable. And of course, this is something we do in our field projects all the time. We don't give people the full bandwidth because we can't send it. But any other ideas on other types of real-time data we might look at?
Along those lines, you have power spectra or co-spectra.
Yeah, right. Power spectra, co-spectra.
Spatial interpolations from distributed networks.
Oh, there you go. For products. Yeah.
That's kind of a slippery slope about getting into the analysis side of things, because then you start putting together a cookbook of very specialized things. There's things for some people and other people you don't have it. We've tried to avoid getting real specialized.
I think one thing I'd say is perhaps the analysis teams, develop the products. Maybe they take the spatial data from the CHORDS portals in the area, develop the products, and then those go out through another CHORDS instance. And maybe something like that would work. Yep.
Or maybe plugins that they could provide.
Oh, that's a good idea. With an open source. Yeah.
I think you have to think of real time in a little bit different perspective, and that is that a lot of the things that we're trying to do in meteorology is we're trying to forecast what's going to happen in a specific place. And you're talking about real-time data. If I can access the forecast for the time that is now from different models, I can see which model is providing me with the most accurate result.
Yeah.
And that's just a lookup sort of thing. And you've got things like weather stations or aircraft or whatever, but they're geographically spaced, and they're sampling at a given time a real variable.
Right.
And you want to be able to compare that with
the model.
Different kinds of model output to see which model is producing the right output. And so this kind of a structure lends itself to being able to do that for a variety of different locations that might be really useful. If you do it for one location and one model, you can do it easily for a dozen locations.
Right. Common interface. Yep, Dan?
If you had that comment to that, the 25 hertz observations, I was thinking of maybe that if there's a time series that's very high temporal resolution, that you could do like a Fourier transform, break it into components, and just store the components. And that way you have sort of a time series at much lower temporal steps.
That's a good idea.
Preserve the high sampling rates.
That's what they did with the BAO 2 decades ago. when they're limited by storing data on how
Yeah.
they
Simple correlations, very disparate data sets looking at.
Yeah. Geosciences, yeah. That's a great example, yeah.
Yeah, I think these are great ideas about how we distinguish ourselves from the Internet of Things.
Yeah, right. The types of things we're trying to do with that data are quite different. Those are great. All right, thanks so much for that feedback. that's all I had for the presentation. Check out chordsrt.com, and here's the email address for the team if you have further questions. And I really appreciate your suggestions, and thanks for being here. Thanks.